Hi, everyone, and welcome to People Behind the Science. I'm your host, Dr. Marie McNeely, and I appreciate you joining me today for episode 755 with our guest scientist, Dr. Carlos Portela. Listeners, if you like this episode and you want to check out more stories from amazing people doing great science, you can find more episodes of our show on Apple Podcasts, Spotify, or wherever you like to listen. And today, Carlos has some excellent stories to share with all of us. So get ready to meet another one of our brilliant people behind the science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to People Behind the Science. Listeners, today I am thrilled to be speaking with our guest scientist, Dr. Carlos Portela. So, Carlos, welcome to the show today. How are you?
I'm great. Thank you for having me.
Well, thank you so much for joining me, and we're looking forward to learning more about you and your work in our conversation today. But let me first start by telling our listeners a little bit more about you and how you got to where you are today. So listeners, Carlos is the Brit and Alex Career Development Professor in Mechanical Engineering at MIT. He received his bachelor's degrees in aerospace engineering and physics from the University of Southern California, his master's and Ph.D. degrees in mechanical engineering from the California Institute of Technology, or Caltech. And Carlos remained at Caltech to conduct postdoctoral research before joining the faculty there at MIT. And he was the recipient of an NSF Faculty Early Career Development or Career Award. And he has also been named among MIT Tech Review's 35 Innovators Under 35. And today, Carlos, we are excited to get to know you, of course, both as a scientist and engineer, but also as a person more generally. So can you tell us, what do you like to do when you're not doing science?
Absolutely. So, of course, that has been a fluctuating set of hobbies depending on how busy things get, and also the weather, I will say, being in Boston. But I generally like to stay active. So I like to run quite a lot. Also in the summers, I like to play golf, team sports in general, I really enjoy. And also when it's not exercise, I enjoy food a lot. So trying out new restaurants and really exploring the food scene in Boston is something I've enjoyed doing quite a lot.
Phenomenal. What are some of your favorite foods there in Boston?
I really like fusion cuisine. So whenever there's a really cool place nearby that mixes Asian food with Spanish food, and I really like that.
Amazing. Well, I love it. I think getting out there, getting some exercise, having some fantastic food is a great way to sort of expand your world outside of the science. But the science you are doing is very cool. So let's talk about that as well. How do you describe your research to someone who's outside of science or engineering?
So at the very general level, I think what we do is designing, fabricating, and testing new types of materials that have unconventional properties. But the essence of what we do really is taking materials that we already know how they behave and already exist, but rather rearranging them in interesting ways in 3 dimensions. The tricky thing is that we do this at the nano or micro scale. So these microstructures, 3D microstructures that we can design, and generally we start with designing them on a computer. We can make them be so small and then repeat them many, many times. So you end up with an overall architected material, which is what we call these interesting materials that we design. The reason why we do this and why we have a lot of fun doing this research is that we're discovering ways in which these 3-dimensional shapes at those small scales actually determine how a material will feel at the macro scale. And that means that it has really interesting stiffness properties. You can imagine things like a material that has the stiffness of a metal, but can be extremely lightweight. And there's also other interesting behaviors, such as unique ways of propagating sound or ultrasound, depending on the frequency. And also, we're interested in designing materials that absorb a lot of energy upon impact. So you can imagine better helmets and better protective structures.
Very cool. Well, Carlos, I look forward to digging into some of the details throughout our conversation today, but I'd love to take a moment to talk a little bit about motivation. I think as a scientist and an engineer, the work you do is quite inspiring and motivational in and of itself. But do you have a favorite quote or a saying or something that really keeps you motivated?
I wish I had a great answer in terms of having a quote that really has driven me all these years. I don't, but I will share with you one that I heard recently, and I'll give you also my interpretation of it. And I don't know exactly who to attribute this to. I just heard it in passing, which was that it doesn't get easier, you just get better. And what really struck me with that, and in particular, the science that we do, us scientists, like, it's not like we're superhumans and know how to do everything and we still make mistakes. I think what really struck me is that when we start doing new projects, it seems like things get easier, but science is never easy. It's just that we've developed some skills day after day that really allow us to tackle our research problems in a maybe more efficient manner. So really, it's just, I like sharing that idea because, especially to my newer students, at first, it's going to be extremely hard, but they'll get better and they'll know how to tackle big problems in a much more enjoyable and efficient manner.
Absolutely. And I think those experiences along the way are all part of the journey.
Yes.
Well, that is a fantastic motivational quote. And I think as a scientist, and particularly working at a place like MIT, you get to work with a lot of really inspirational, amazing people. So, Carlos, when you look at the people around you or the people over your career path who you've worked with, are there particulars who really rise to the top of your mind as mentors or role models or individuals who've really had an impact on you?
Absolutely. I think we all learn from watching those above us tackle hard problems and address questions in a certain way. In my case, I had the luck really to be co-advised in grad school. So I got 2 role models there basically for free. But I will say throughout my career, I think there's 4 mentors that really come to mind, starting from my undergraduate career. I think my undergraduate advisor, research advisor, really was the one who really motivated me to go to grad school, or even consider it. It really wasn't in my plans at the time. And then at Caltech, undergrad, Andrea Hodge was my role model and really pushed me towards going into academia. And then while at Caltech, my co-advisors, Julia Greer and Dennis Kochman, 2 role models, each experts in what they do, but also different, right? So I was able to learn how to tackle situations differently from each of their perspectives. And then more informally, still at Caltech, Professor Chiara D'Araio served kind of as an informal mentor, especially when trying to make the jump into the job that I'm doing now. I think something that's kind of remarkable in science, and unfortunately it's atypical to say that you can have so many female role models. That's of course changing and hopefully will change. But in my case, that was very unique. I'm lucky to have had so many fantastic women scientists around me. And I think that has made me potentially a better advisor for women that are in my group. And I hope to continue learning.
Absolutely. Well, it sounds like you've had some wonderful mentors along the way. And you hinted that perhaps grad school and academic science was not part of the original plan. So I'd love to hear more about where this interest in science began and what those original plans might have been. So can you take us back to the beginning, Carlos, and tell us what first got you interested in science?
So I'll take you back to when I was maybe 3 or 4 years old. And this all really gets sparked with my passion for aviation and airplanes. Mm-hmm. Since I can remember, I think that's been what really intrigues me. And then early on, I heard somewhere that there was this major, this career, something you could study that was called aerospace engineering, and that it would allow me to potentially design airplanes. And I was probably 10 at the time and just said, okay, that's exactly what I want to study. So that's where really the interest in engineering came from. And then I went into my undergraduate studies. This was at USC, and I ended up double majoring, doing, of course, aerospace engineering and then physics. But then later on, and this was, I will say, later than I would have wanted it to be, I got involved in research. And this was a lab that did a lot of nanomechanics. So it's basically understanding the mechanical properties of materials that have nanoscale features. So this could be special metals, for instance, that have nano inclusions or thin films at the nanoscale. So these are very advanced tools for an undergraduate, but I was able to learn little by little more about this mechanical behavior of materials world. And then at the time, I thought what I wanted to do is go work for some aerospace company and continue my dream of building airplanes. But then, as I was mentioning, my advisor suggested that, no, I would be okay at grad school. So I decided to give it a shot. I sent out a few applications. And then, I was lucky to have been admitted to Caltech. And it was an easy move. So USC is in LA, downtown LA, and Pasadena, which is where Caltech is just 20-minute drive from there. So the move was easy. No big change was necessary. So I said, okay, maybe let's just go with the flow.
So how did it go? How was your experience at Caltech?
So Caltech is a very special place in many aspects. Of course, there's great scientists there, but what is particularly unique at Caltech is the size. It's actually a very small institution. At the time, it was probably 1,200 graduate students and 800 undergraduates total, which made for a very different experience from USC. And also just everything that you studied there was at a much higher level than what I was used to. So at first there was, of course, a little shock. But then as I got more comfortable with how the place runs, I started really enjoying my experience at Caltech. So I was able to learn from great scientists, and really there was no limits in terms of what classes I could take and what topics I could be interested in. So fantastic place. So after that, doing my PhD and master's first, I started working on experiments, but then with my co-advisor, Dennis Kochman, started doing some computational work, mechanics work. And then I would say year 5 of my PhD, I wasn't sure exactly what I wanted to do career-wise. So I started applying for jobs, a lot of technical consulting jobs, which were very interesting jobs. Once I went through the interview and even was lucky enough to get an offer, I still was not convinced that that was exactly what I wanted to do. And I will say it wasn't until my defense. So how it goes is that you write your thesis, and that's a hard process. It takes many, many months. And then typically once you hand in your thesis, you have a couple of weeks to come up with your thesis defense, the slides or the story that you're going to tell. And I really enjoyed that part. So it was about 3 weeks where I was thinking of how do I tell my scientific story, what I've done over the last 5 years. And when I was done with the defense, having really enjoyed that process, my advisor, Julia, came up to me and suggested that maybe I should reconsider applying for academic jobs.
They didn't want to let you go.
Exactly. And at that point, I realized, and I really enjoyed that process. I feel like an academic job has a big component, which is telling scientific stories and creating new pieces of knowledge. So I went for it. And that's when I sent all the applications, and this one ended up working out.
Oh, absolutely. And I know there at MIT, you are doing some phenomenal research. So I'd love to talk about some of your projects. So Carlos, do you have a particular project that you are working on at the moment that you are just the most excited about?
It's hard to say if I have a favorite one. I will say there's a couple of big thrusts or general directions that my group is going in that I'm particularly excited about. The first one is this field of architected materials, which I described earlier. It's a fairly new field, I would say maybe a decade or so, maybe 2 decades. And recently, we've been able to do a lot of great work as a community because we have these very nice additive manufacturing tools, like 3D printing tools that allow us to craft any sort of material structure that we can imagine. The issue with all these advanced tools is that a lot of the times we're testing materials that basically look like a speck of dust. They're so small, very intricate, and we can learn a lot from them, but they're not really at the scales that we need to really broadly apply them. So one of the thrusts in my group really is to try to overcome that bottleneck, coming up with ways to scale up the fabrication of architected materials. So what we're saying here is maybe let's put our nice tools to the side for a second and let's leverage processes in nature that undergo self-assembly or self-architecture that could potentially give us these 3D morphologies that are quite interesting from a mechanical perspective. So here we're leveraging these basically polymeric mixtures that once we heat them up, they create these intricate 3-dimensional patterns. And in a matter of minutes, maybe an hour, we're able to get cubic centimeter volumes of these materials, which are way, way bigger than anything that we can print. And we're learning a lot of mechanics from these. Then the second thrust really has been this motivation for studying and understanding how these architected materials behave in real life conditions. And what I mean by that, we're limited when we study them in the lab. Sometimes we're very limited to deforming them in a very, very slow manner, what we call quasi-static deformation, and extracting the properties in these slow deformations. But realistically, if we're trying to apply these materials, sometimes, say they're a coating on a helmet or they're the helmet itself, sometimes they'll get dropped, and the helmet naturally will need to absorb some dynamic impact. But so far, we have not been able to measure the mechanical properties of these materials under high rate deformations. So we're developing techniques to understand how these materials behave under these fast deformations. And the other aspect that we're doing is because we're testing still at small scales, we're coming up with high throughput testing methods. And the reason why this is important, if you imagine trying to do dynamic experiments on materials currently at the centimeter scale, generally, it will take you hours to print that sample. And then it'll take you maybe half an hour to an hour to do every single dynamic experiment, meaning that in a day, you've probably collected on the order of 10 data points. But we're doing these at small scales, and our tools are able to do these tests one after the other. So we end up being able to do hundreds, if not thousands of data sets or data points in a day. And that's currently a big bottleneck we've had in experimental mechanics, is getting enough data of materials so that hopefully these data sets can then be used into all these amazing machine learning algorithms that have not yet been fully applied in material science and mechanical engineering.
Oh, very cool. So now that you're testing kind of on the order of 100 to thousands of different architected materials or samples of architected materials per day, how do you make that decision of which ones are most interesting to proceed with developing further?
We generally start our experiments with some physics intuition, and generally it's guided by some simulation that we've run before. And from there, we can come up with subsets of samples that we expect something interesting to happen. But also the luxury of being able to get a lot of data sets is that maybe we don't have to be too careful or too restrictive in terms of what samples to test, because it's a 5-minute commitment to do each sample. And then the data will probably guide us in the right direction.
Well, that makes sense. Well, these are some really cool projects, and I think you talked about them in a way that makes it sound like it's easy and that everything goes as expected. And I think that is just not the case in science. So, Carlos, we love talking about the struggles, the failures, all of the behind the scenes things that happen in science, because I think people don't often get to see that part of the story. So do you have an example of a major challenge that you faced or a big failure that you've had to recover from? And if so, can you tell us about it?
Yes. I mean, there's many difficult parts of a PhD, but I can recall one that was particularly tough. So when making these samples, and I've described them already, they're microscopic. So we can't see them really with our eyes. And also to characterize them, to check whether they're exactly what you wanted to fabricate or not, we have to put them under a scanning electron microscope. But even then, you're just taking superficial pictures of these samples. So in this work that was towards the end of my PhD, we were really going in a new direction. This is something that I was very passionate about. I was lucky enough to get the freedom from my advisors to really explore this new direction of looking at this dynamic response of architected materials. And this experiment really consisted of having these microparticles get accelerated at supersonic speeds and hit my architected materials. And from there, we can record these with a high-speed camera, high-speed microscope, and then we would extract some mechanical properties of energy absorption. The issue was that this is year one, well, full year into this project. We were getting some data. It seemed good. I mean, as with whenever it's the first time you're doing something, you should always be cautious. Always assume you're wrong until you prove yourself right. So we're getting a lot of data, of course, being cautious about it. But then when we're really characterizing these samples, and by characterizing them even deeper, I mean that we had to would cut them in half with a special tool that bombards them with ions and cuts them. So after doing a couple of these cuts, which are of course time consuming, and that's why we couldn't just do that from the beginning, we started realizing that a lot of these samples were actually defective. So they were supposed to be porous and very lightweight, but we actually had solid chunks of the polymer, or in this case, it was carbon that was inside of the material. So all these tests that we've done over the last 9 months, 12 months, basically were not usable. They weren't good data. And I say this happens all the time, but in this case, I think it was a huge blow to my self-esteem and also my PhD as a whole, because I really was excited about this new direction. As I mentioned, it's one of the big things that I'm doing now in my group. So there's two approaches, right? You basically say, okay, this is done and you give up, or you just pick yourself up and then start all over and just with the new knowledge that you just acquired and do it the right way. So this meant that I had to lose about a year worth of work and start from scratch when collecting data from these samples. But I really tested resilience, mental resilience, and it happens a lot in a PhD. I would say that's the biggest tough situation that I can recall in recent memory.
Definitely. And I think you had the absolute right approach there, right? You pick yourself up, try again, maybe go home for the day, try again tomorrow.
Yes, absolutely.
Were you nervous once you discovered these impurities, having to have that conversation with your advisors and say, look, I think we got to start over?
Yes, but that's the magic of being in a positive working environment. I think any advisor, of course, will want to know that instead of it being hidden from them. And the response that I got there was positive, just saying, okay, let's do it right then. And thank you for being careful about checking these. That's another thing. Like in science, I think we shouldn't be afraid of finding mistakes. We should be proud that we were able to find the mistake and caught ourselves before we went too deep.
Absolutely. Well, Carlos, thank you so much for taking us through one of these difficult moments in your career. And I think you're absolutely right. These sorts of situations in some flavor happen to everybody in science. And we just want people out there to know that they're not alone if they're struggling with their research, but we don't want to focus on the downtimes in your career. I'd love to celebrate some of your successes as well. So do you have a favorite success story, whether it was a big win or just a small but particularly meaningful one that you'd like to tell us about?
So a recent one, this is maybe 3 months ago, we were able to publish a new technique that we developed in my group to do high throughput characterization of materials. But what's particularly unique and why it felt like a huge success is that this was completely different from anything that my group had been doing for the last few years. Very different from what I did in my Ph.D., which was doing this characterization of materials in a mechanical sense without ever touching them. The way we did this was able to add some expertise to my group from the optics side of things. And with this postdoc, you and Kai, we were able to come up with this method that used the laser to excite materials at the microscale. So they would basically vibrate. And then with another laser, we were able to actually measure these vibrations that were on the order of nanometers. And then now using the mechanics knowledge that we did have in the group, we were able to then extract a lot of mechanical properties out of these vibrational signatures. So the reason why this is a particularly big success for us is that up until that method, I think primarily the only way that we could characterize materials at that scale was by using what we call a nano indenter, which is effectively just like a large universal testing machine, but of course shrunk down so you can measure small forces and small displacements, which implied you always needed to touch these samples. These tools are generally also limited to slow deformation. But without needing to touch the samples and with relying on vibrations, we were able to do not only dynamic testing because vibrations are dynamic, but also we only needed to pause on top of a single sample for about a minute. And then we're able to collect 10,000 measurements. And then we just move to the next one and collect another 10,000 measurements. So that really increased the throughput and also the amount of information that we could extract. And all of these samples were pristine after doing these tests because we're not permanently deforming them. That was a great success for the group in general.
Oh, that is phenomenal. And I think these kinds of method development projects really have the potential to have a huge impact far beyond your own lab and research. So do you have a sense of what kinds of impacts you would like to see this have on the field?
Yes. So one of the things that we were able to demonstrate with this technique is that just by looking, you can think of these, we call them vibrational signatures, or you can think of it as a vibrational fingerprint. So every structure will have a fingerprint. It will want to vibrate in certain frequencies. And this dream that I've had is that hopefully someone out there is motivated by this and might want to apply it, is that this technique can be used for defect identification, non-destructive defect quantification of microstructures. And here what I would have in mind is something like components on a chip that are being manufactured at scale. In this non-contact way, you could really get live information as to whether there's a defect in your assembly line or not, and really give you much higher throughput in characterizing whether some microscale components are defective or not.
Oh, I think that is so cool. So, Carlos, how did you celebrate this success? I know the publication of a paper is a long process, but how did you celebrate the victory?
Again, with food and great company. So the whole team, we went out for a nice meal. We also reminisced on the process. I think you're absolutely right that especially with big accomplishments, it's generally a couple-year effort sometimes. So we also learned along the process, and we had a lot of fun kind of recapping the lessons learned and the little wins and sometimes the losses that we had along the way.
Definitely. And I think taking a break from the lab, getting outside, having some wonderful food, or reading a good book can be a great way to recharge and kind of come at your science more invigorated. So we love talking about book recommendations on our show. And Carlos, do you have a favorite book that you've read either recently or long ago that you'd like to recommend for all of us today?
So I'm trying to get better about reading for fun.
Mm-hmm.
It's not something I've been doing a lot over the last couple of years, but last year I did read the famous book. It's Unbroken. There's a movie about it. And I just really enjoyed it, partly because it's, of course, a real life story. And just seeing how some people are just really, really strong mentally and physically and are able to endure a lot of tough situations. So it's quite an inspirational story. So I highly recommend Unbroken if you haven't watched the movie or read the book.
Wonderful recommendation. Well, Carlos, we will add this to our website for our listeners to find there. And I think you're absolutely right. Seeing kind of the real life struggles of others can help put your own problems in perspective sometimes.
Yes.
And I think as a scientist, not only do you get to work on really cool projects with wonderful people, you get to go to a lot of really cool places. And I think these opportunities to travel are something that not everyone realizes is part of the career. So, Carlos, do you have a favorite place that you have traveled for science that you could tell us about?
Yes, I do. I was lucky enough to spend a summer in Switzerland for research. And I really enjoyed that. One, I hadn't been to Switzerland before that, so everything was new, and Swiss Alps are fantastic. What I really enjoyed the most was just getting immersed in the European culture, both from a scientific perspective, but also just day to day. I think what I was able to get from that experience is just a better balance. I think in Europe, they really know how to be better balanced than generally you see here in the US. And they still do great work and they still accomplish great things. And for some reason here, we tend to think that we only need to work all the time, 24/7. But I was able to enjoy the Swiss lifestyle in the summer. So that was great.
Oh, it sounds amazing. And I think being able to spend a little bit more time in a place rather than, a week conference trip is a great way to really, like you said, get immersed in the culture and experience more of the different things in the area. So were there particular things that you saw or did in Switzerland that you would really recommend if people are able to travel there?
Yeah, so a lot of these were because I coincided in the right time, but in Zurich, which was a city where I was, there's one day of the year, maybe it's one weekend, but maybe I think it is just one day, where you're allowed to swim across the big Zurich Lake. And I swam when I was a kid, but I hadn't in a while. But I got there and there was that opportunity and decided to swim across the lake. And that was quite unique. I think I talked to people that are from Switzerland or Zurich even, and they haven't done that. So that was a quite special thing that I was able to do. And I did a lot of hikes. Switzerland is gifted in terms of beautiful mountains and hikes. So I was able to do that quite a lot.
Oh, wonderful. Well, listeners, definitely take some time to explore the outdoors if you can make it over there to Switzerland soon. And we've talked about some of the mentors that you've had, the people that you've worked with over the course of your career. And I think oftentimes people are surprised when they get to know distinguished scientists or scientists in general because they don't meet the stereotypes that they had in their head about them. And I think dispelling some of these media myths about scientists is really important. So we love breaking some of these stereotypes. And Carlos, do you have an example of this human side of science, whether it's a quirky lab tradition or just a fun or funny memory that you have with colleagues that you can share that really showcases this human side of science?
Yes. In my group at Caltech, there was this tradition of, I think there was actually a couple of people on this committee of cake baking for people's birthdays. And these cakes were not your typical cake. I think a lot of the times these cakes would try to convey the personality of whoever birthday it was. So as an example, for instance, sometimes we did fruit as cakes for birthday. So huge watermelon slices with candles, just because the person just really enjoyed fruit. I had a colleague in grad school who enjoyed working out a lot. So our task there was to try to make high protein cake or baked goods, only high protein things. That was quite a lot of fun. So yeah, anything that would bake, no pun intended, we would try to bake their personality into the cake. And being a young group, so I started at MIT in 2020. So of course it takes some time to start building a group culture, but I think in recent years, I've been able to see a little bit of that. So something that we do maybe twice a year is some sort of gift trading activity, like a Secret Santa when it's the holidays. And in that sense, we're able to also really celebrate everybody's unique personality. So you really would pick someone that maybe either you know really well and you're able to get a fantastic gift that's just perfectly suited for them. So yeah, there's a lot to science that is not just working, but really the personal interaction. So that's what these activities really help us capitalize on.
Absolutely. And I love, like you said, that each group kind of develops their own personality and culture. And it may shift over the years with the people who are in the lab. But I think, like you said, it really captures the essence, this sort of sense of humor, sense of fun, and the personality of the people in the group. And I think that is phenomenal and something that I've really enjoyed in working with scientists as well. And I know we've talked about some of the different projects that you've been working on lately. And I know in science, you often face barriers, right? If it was easy, everybody would be doing it. So things like funding, staff, technology, feasibility, time, whatever the case may be, often hold you back, Carlos. So if we took away the barriers that normally hold you back, what is the one research question that you would want to answer most?
That's an easy answer for me. And it's not one question. I think I would have many, many questions, but it would all be around one theme. And I think food science has always been very intriguing to me, partly because let's think of something like bread, for instance. Bread itself is an architected material. It has some microstructure, and the microstructure really determines how stiff the bread is, how it tastes. And I don't know if this has been characterized systematically from a scientific perspective. I think if funding weren't a thing, there's a lot of fun questions to answer relating food, their microstructure, and the sensory experience whenever you eat it. There's also a lot of being a solid mechanician, meaning I'm trying to understand how solids deform. There's a lot of high rate deformation that's related to food, for instance, popcorn. So trying to understand those processes systematically and with the right equations, I think that would be a fascinating question to answer. But yes, funding would be the tricky thing.
Absolutely. And I think, of course, building on your hobby of trying cool foods and being able to implement this project would be exciting.
Absolutely.
Well, wonderful dream project to propose for us to think about today. And I know we've talked about some of the people who have mentored you along your journey. And I think these people can be great sources of advice. And I think advice can really help you get out of a sticky situation in your career. So we love sharing advice with all of our listeners out there. So Carlos, when you think back over your career, is there one piece of advice that really rises to the top of your mind as just the best or most helpful piece of advice you were given?
The big part of this job that I'm currently doing is really understanding how to best devote my efforts. And I think the advice that I got early on is, of course, don't try to do everything. There's only one of you, and there's many, many, many things that people will ask you to do. So sometimes it's okay to say no. And I'm also a bit of a perfectionist at times. In some scenarios, like you don't need to be that high attention to detail. There's some scenarios where you need to know when to spend your 100% or when 80% will get you there. And then you can spend that 20% in some other direction that is really needed. So that has been maybe the piece of advice that I keep replaying in my head. I'm still working on it. It's still very hard to be able to do the very best in everything that we commit to. And I think this applies to not just the job that I'm doing. I think everybody's busy. Everybody has many, many responsibilities at once. So I think this could apply to all of us.
Oh, absolutely. I think this is something I'm working on myself, and it can be hard to kind of make that decision of when to say no. What are the opportunities you should say yes to for sure? What are the opportunities you should maybe turn down? And I love this point that you make about being a perfectionist. How do you decide what is good enough for a particular item? So do you have any advice on how to make these decisions or how to really implement this into your life?
Maybe the question I ask myself is, will anybody else notice besides myself, right? Because I feel like it's not good enough for my standards. And if the answer is maybe some people will notice or nobody will notice, then that's an indicator that it's okay with the state that it's in. That part is also hard. I don't think I have a great rule yet.
We'll stay tuned in case you think of it. Yes. And I think you're absolutely right there. I think kind of making those decisions is difficult, and it may depend on the situation as you go through it. So wonderful piece of advice for me and our listeners. Is there any other last piece of advice, Carlos, or a last note of inspiration that you would like to end our conversation on today?
So I will try two pieces of advice. One, particularly to young listeners, is that it's never too early to get involved in research or science. And I think there's a lot of great opportunities, even now with the internet being as accessible as it is, to really learn about scientific concepts. Don't shy away from science. There's science in everything. And the more you try to get involved with it, I think it gives you a unique perspective. Even if you're not going to pursue a scientific career, I think just understanding it really helps. And then the second thing is just in general to the rest of the listeners, I would say, and this is something that I've learned throughout my scientific career, is that we're always our harshest critics of our own work. And science is always a learning process. And the first product that you will create in a scientific sense is never going to be perfect. And you have to be okay with it not being perfect and learning along the way. And just with the hope that the next iteration of whatever you do will be slightly better. So to summarize that is just be nice to yourselves and embrace the opportunities to learn and improve.
Absolutely. And don't be afraid to put those ideas out there, even if they're not kind of 100% clean.
Exactly. Yes.
Well, I think that is a fantastic note for us to end on. And if our listeners want to learn more, Carlos, about you and the wonderful work that you're doing, what is the best way for them to do so?
The best way would be to visit our group website, which is portela.mit.edu. And Portela, just like my last name, Portela. And also, from time to time, I'm not too active on social media, but on my Twitter or X account, I sometimes share a lot of our scientific accomplishments. So that's a good way to follow us as well.
Outstanding. Well, listeners, definitely check out that website, get connected with Carlos. And Carlos, it's been such a pleasure to chat with you today. Thank you so much for your time.
Thank you very much, Marie.
Well, it was wonderful to chat with you, and listeners, great to have you here with us as well. We hope you'll join us for our next episode of People Behind the Science.